Everybody. Today in this video, we're going to go over the review sheet for quest number 4, which is a cross between a quiz and a test. It is going to be a full period, but it's going to be shorter than a test and count as half of a test. Question number 1 says, in the diagram below, 4 pairs of triangles are shown. Congruent corresponding parts are labeled in each pair. Using only the information given in the diagrams, which pair of triangles cannot be proven congruent? So we need to put an answer and an explanation. So let's take a look over here. So in answer choice A, I'm going across and I see side, side, angle, side, side, angle. That's S, S, A. If I go around the other way, I have ASS, ASS. Moving over to the second one over here, answer choice B, I have ASA, angle, side, angle. Let me write that down here. The third one, C, I have AAS, angle, angle, side. And finally here, I have two right triangles. I have congruent hypotenuses in both of the right triangles. Remember, the hypotenuse is across from the 90-degree angle. So here the hypotenuses are congruent. And we also have a pair of congruent legs. So we have HL here. So SSA is the method that is not valid for proving triangles congruent. If you read it backwards, that's ASS, which is not something you want to be writing on your geometry test. It is not a valid method of proving triangles congruent. So let's write here answer choice A. And in my explanation, I'm going to write side angle is not a valid method for proving triangles congruent. And that's perfect. There we have it. We are all done. Let's move it forward. So number 2 is a proof. So let's come up with a plan for the proof first, and then we'll write it up. So we have that DA is perpendicular to AB. So I'm going to draw in a right angle because we all know that perpendicular lines form right angles. And I know that CB is perpendicular to AB. So here, let me draw in my right angle where CB and AB meet because, as we know, perpendicular lines form right angles. And then we have the information that AD is congruent to CB. And our goal is to prove that AC is congruent to BD. So let me highlight AC for a second. So AC is right over here. And we have information about CB and about this right angle over here, which are all part of triangle ACB. We also need to prove that BD is congruent to AC. So let me highlight BD. And if we take a look at BD, and we also take a look at AD, which we have information about, and about the right angle here at angle A, which we have information about, those are all parts of triangle DAB. From taking a look at what we're trying to prove and from our givens, I see here the two triangles that we're going to be focusing on. So our plan is going to be to prove the purple and the green triangles congruent. Those are the triangles that we're interested in. And then after we prove them congruent, it'll be one more step of our proof to prove that AC is congruent to BD. AC and BD are sides of each of the two triangles. So once we know the triangles are congruent, we'll also know that AC and BD are congruent by CPCTC. Whenever two triangles are congruent, their corresponding sides or angles are also congruent. And that's what CPCTC means. So in order to see things a bit clearer, I'm just going to take each of our overlapping triangles from the diagram and just draw them separately. So we have DAB, and let me draw the green triangle separately as well so we can take a second look at that a little bit better. CAB. I just want to mark in these separated triangles what we already had in the diagram. And of overlapping triangles, we're going to look out for a shared side or angle. That means a side or angle that's in common in both of the triangles. And I see in my diagram here, since I used color, that side AB is highlighted in both green and purple. And if I take a look at the separated triangles, I see the side AB is AB in the purple triangle and is AB in the green triangle. So since it has the same letters in both of the triangles, AB and AB, we can tell that they're the same sides of the triangle. So it's even easier to see that it's the same shared side when you separate the triangles and look and see that the letters are the same. So two good strategies for working with overlapping triangles: color coding and drawing the triangle separately. Okay, we have all the information we need. This will be SAS, SAS. And then from there, it will be one more step to prove AC congruent to BD by CPCTC. So let's get writing our. So I'm going to try to do this as neatly as possible. It is very hard to write on here. So my givens are DA perpendicular to AB, CB perpendicular to AB, and AD is congruent to CB. So I'm going to put here that that is given to us. Okay. From the givens, we had the blue pair of sides, AD and CB. So I'm just going to label that a side so that we know for sure we already have that pair of congruent sides for SAS from our givens and our givens alone. Now we need to mention the right angles. We have information that we have perpendicular lines from the givens, but in our diagram, we marked that we have right angles. So that also has to be inside the actual proof. So I'm going to call this right angle over here angle A. And you can also name it with 3 letters. Always better to name with 3 letters to avoid any confusion, to be as precise as possible. In this situation, it doesn't matter. Angle A is the whole angle A that we're talking about. But in order to be absolutely sure, whenever in doubt, just name with 3 letters. And angle B are right angles. And I'm going to put here as my reason: perpendicular lines form right angles. We knew that we had perpendicular lines from the givens, so now we're drawing the conclusion that our right angles were formed. And since we want to use these right angles as a pair of congruent angles for SAS, that's going to be our A part of SAS, we actually do have to say that these angles are congruent to each other. And since they're both right angles, since we already proved that, we can simply just write all right angles are congruent, and that works. All we need after that is the shared side AB that was shared between the two triangles. Since it's shared or the same in both of the triangles, we can say it's congruent to itself. That will be by the reflexive property. From there, we can say that the two triangles, so the purple triangle, I'll call it triangle DAB, is congruent to the green triangle CAB, and that is by SAS. Just to verify, we have all the information that we need for SAS in our proof. We have that first pair of sides in blue from our givens. From step 3, we said angle A was congruent to angle B since they were both right angles. So that gives us the A that we're using for SAS. And then from step number 4 with the shared side AB, that is the last pair of congruent sides that we're using for SAS. We have our 2 pairs of sides and our angles that we're using all mentioned in the proof. From there, it is one more step to say that AC is congruent to BD, which is what we actually need to prove. And we already talked about that this is going to be by CPCTC. Now that we already have proven the 2 triangles congruent, we can definitely say that this pair of corresponding sides, this side and this side of each of the triangles is congruent because we already know the triangles are congruent. So the corresponding sides are also congruent. Corresponding parts of congruent triangles are congruent. For number 3, we're given the vertices of triangle PQR, so I just went ahead and plotted those on the graph. And the first thing it tells us in this question is that points A and B are the midpoints of PQ and RQ respectively. So I know in order to find point A and point B, since they're the midpoints of PQ and RQ, I have to find what the midpoints of these line segments are. So the easiest way to do that is to plug into the midpoint formula. So I'm going to find the midpoint of PQ first, and then I'll find the midpoint of RQ after that. So let me plug into the midpoint formula. So that's the average of the x's, comma, the average of the y's. So with P and Q, I'm going to add the x coordinates, which is -3 and -1, divide them by 2 to average them, and the y coordinates are -1 and 7. Okay, and we get that's -4 divided by 2 is -2. That is 6 divided by 2 is 3. And for RQ, let's average the x coordinates. That's 3 and -1 divided by 2. And if we average the y coordinates together, that is 7 and 3 divided by 2. So that gives us 1. 2 divided by 2 is 1. And 10 over 2, which is 5. So let me graph these on the graph really quickly. So -2, 3, -1, 2, 1, 2, 3. And that looks like it's in the middle of points P and Q. It should be, and I'll label that as A. Oop, that doesn't look like an A. Let me try that again. There we go. And the point 1, 1, 2, 3, 4, 5, right over here, should be the midpoint of QR, and I can label that as point B. So now we've found points A and B. We have their coordinates right here. I'll label this is point A and this is point B, so we know that. It says use coordinate geometry to prove that AB. So I need to have a line segment AB. So let me connect these together. So we're proving that AB is parallel to PR and is half the length of PR. So let's start with the parallel part first. So if we're showing that AB and PR are parallel to each other, we have to show that the slopes are the same. So let me just label what I'm doing here. I'm showing that AB is parallel to PR. So what I'm going to do is I'm going to find the slope of AB, and I'm also going to find the slope of PR, and I'm going to show that they're the same. So remember that in order to find slope, we subtract the y values, divide by, subtract the x values. So the y values for points A and B are 5 and 3, and the x values are 1 and -2. So I got 2 in the numerator, 3 in the denominator. When I find the slope of PR using points P and R, I should find that the slope is the same. The y coordinates are 3 and -1 of P and R, and the x coordinates are 3 and -3. That gives me 4 over 6. And if I reduce, that gives me 2 over 3. So we do have the same slopes here. So I'm going to make a concluding statement that supports my calculations here. So I'm going to say AB is parallel to PR because they have the same slopes. Now I also need to show that AB is half the length of PR. What I want to do is I want to find the length of AB and I want to find the length of PR. And I want to show that AB is half PR's length, which would mean that PR would be double what AB is. So that's going to require the distance formula. I'm going to have to find the length of AB, and I'm going to find the length of PR, and then I can compare them. I'm trying to give myself plenty of space here. So I'm going to use the distance formula, and I'm going to plug in points A and B first. So my x coordinates are -2 and 1, and my y coordinates are 3 and 5. Remember to bring down your radical. -2 minus 1 is -3, squared is 9, plus 3 minus 5 is -2, squared is +4, and that gives me radical 13. Okay, let me plug points P and R into the distance formula. So the x coordinates are 3 and -3. And the y coordinates are -1 and 3. Remember to bring down your radical. -3 minus 3, that is -6. Squared is 36. Plus -1 minus 3 is -4. Squared is 16. 36 plus 16 is 52. So I'm having a hard time because these have radicals here. I'm having a hard time seeing if radical 13 is half of radical 52, or if radical 52 is double radical 13. So it might be helpful. I know we don't type radicals into our calculator usually, but it might be helpful to go ahead to your calculator and type in radical. Actually, I can show you on my calculator. Give me 1 second and I'll pull up my calculator. So I'm over here on my calculator, and all I did was type in the square root of 52, so radical 52 divided by radical 13, because I want to see if radical 52 is double radical 13. I want to see if one is half of the other. And when I hit enter, I do get 2, which tells me that radical 52 is for sure double radical 13. So that's a way to tell for sure that one is double the other, using your calculator, because it is kind of hard to tell with radicals. Another way that you could have figured that out is if you simplify this radical over here. And what you would need to do is to find the largest perfect square that goes into radical 52. And that breaks down into the square root of 4 and the square root of 13. 13 times 4 is 52. And this simplifies to 2 radical 13. So you can clearly see now, when we simplified the radical, that PR is double what AB is. So AB is half of PR. But the calculator is an easy way to see that also, especially if you don't remember how to simplify radicals on a test or the Regents exam. So I'm going to put a concluding statement that summarizes what my calculation shows. I'm going to just write here, AB is half the length of PR. And I think that's a pretty good explanation here because my calculations show that for sure. The calculations here show the length, and my concluding statement is explaining what these mean, which is that AB is half the length of PR, which is what we're trying to prove. Okay, let's move on to the next question. So we have isosceles triangle ABC. So I'm going to go ahead and draw a picture. Very first thing I'm going to do, I'm going to make my triangle ABC. I know it's isosceles, and they're telling me that AB is congruent to BC, so I mark that in my diagram. Angle A is x plus 10, so let me go ahead and mark that over here. And angle C is 2x minus 20. And what we have to do first is find the value of x. Well, this one's pretty straightforward because we know that in a triangle, if we have two equal sides, the angles opposite those equal sides are also equal. So we can simply make an equation that says x plus 10 is equal to 2x minus 20. Don't get stuck on solving the equation. Let's move this x over so that we can have the x's in one place. So that's 10 is equal to x minus 20. And then let's add 20 to both sides to get the x by itself. And we get that 30 is equal to x. So I'm going to put that here, 30. The second part is asking us to find the value of angle A. So I'm going to take this x value and plug in for angle A, which is x plus 10. 30 plus 10 is 40 degrees. So angle A is 40 degrees. Okay. Let's move on to number 5. So it says the diagram below shows triangle ABD. BE is perpendicular to AD, and I see that they already drew a right angle in for us, which was very nice. And they also tell us that angle EBD, so EBD right over here, is congruent to angle CBD. So CBD is the angle here that's outside the triangle. They tell us that angle ABE is 52 degrees, so I'm going to mark that as 52 degrees. And wait, if we know these two angles, I labeled my diagram incorrectly. So this here is angle EBD. ABE is right over here. So very important to check over your work. Make sure that you mark the diagram correctly. Very easy to make that mistake. So ABE is 52 degrees, and we need to find the measurement of angle D over here. Well, let me try to figure out anything I can at first that might help me. So first, I'm going to start off in the smaller triangle over here. I already know two angles of this triangle. I have the 90-degree angle and the 52-degree angle. Since I know all the angles of a triangle add to 180, I can definitely find the last angle of the triangle there. Let me do 52 plus 90. That gives me 142. And let me subtract 142 from 180, and I get 38 degrees. So let me put that here. Oops, I don't want to use yellow. 38 degrees. Okay, so these two angles over here form a linear pair. So if this one's 90 degrees, this one also has to be 90 degrees to make 180 degrees. Also notice how all three of the angles here are supplementary. All three of these angles should add up to 180 degrees. And since these angles are the same, we can give them each maybe a value of x. Since they're the same, we knew they were congruent from our givens. And I can set up an equation that says 52 plus x equals 180 degrees, or you can subtract 52 from 180 and then just divide by 2. Same exact thing. So we have 52 plus 2x equals to 180. Let's solve for x. Notice we're doing all the steps that I said before. All we're doing is subtracting 52 from 180. That's our first step. That's 128. And then dividing by 2 because both of these angles are equal to each other. So that is 64 degrees. So we just found that instead of putting x's here to represent these angles, that each one of these angles is actually 64 degrees. 64. There we go. And now that's really helpful to us because now we can focus on the triangle that has angle D, which is the angle we want to find the measurement of. We know two angles of the triangle, so we can definitely find the third one. Let me add 64 and 90, and I get 154. And let me subtract 154 from 180, and I get 26 degrees over here for angle D, and that's my final answer. That's what I am looking for. Okay. In the diagram below, identify all the corresponding congruent parts, then state the postulate that makes the triangles congruent. Okay, so let's do sides first, and then we'll do the angles. So I see GJ that has two congruence marks on it is congruent to HK that has the same congruence marks on it. I see JK down here and GH over here with the same congruence mark on them. So let me put JK is congruent to GH. And then I see the shared side between the two triangles, GK. So I can say that it's congruent to itself. We know that's by the reflexive postulate. Now let's talk about the angles. So I see that we have angle J congruent to angle H. Oh, and I see that there's many postulates that we can use here based on the information that we have. I also see angle G and angle K marked, but angle G is bigger than the triangle that it's in, and angle K is also bigger than the triangle that it's in. So I'm not going to put those because those angles are not inside of the triangles. Of course, once we prove the triangle's congruent, all of the other corresponding sides and angles are also automatically congruent. That's by CP/CTC. But I'm just going to list for now the ones that we know are congruent because we are trying to state how the triangles are congruent. So I'm guessing that at this point we don't know the triangles are congruent because we're trying to show that with a postulate. So I see that the triangles are definitely congruent by SSS. I see 3 pairs of congruent corresponding sides, and I also see SAS, SAS as well. So either one of these would definitely work here. SAS doesn't need any extra information. SSS needs the extra information of GK being congruent to itself by the reflexive property since it's the shared side. So there's a little bit of an error in this question because it tells you the length of AC and AB, but then it's telling you the final length of AB, which you already know. So we'll just go ahead and change that to BC, which is the missing side of the triangle. So I have triangle ABC. I know that angle A is congruent to angle B. AC is 11. AB is 7. And we need to find BC. So let's check it out. We have 2 congruent angles in this triangle. We know that when we have 2 equal or congruent angles, the sides opposite from those angles are also congruent. So the side opposite from this congruent angle is 11. So the side opposite from this congruent angle should also be the same, or 11. So the length of BC should definitely be 11. That's the converse of the base angle theorem. If we have 2 congruent angles in a triangle, the sides opposite those angles are also congruent. Okay, let's move it along over here. So we are given that AD is parallel to EH. So here's AD, here's EH. They're parallel to each other. Let's find the measurement of angle I. So angle I is over here at the very top. So I want to indicate that's what we're finding. So I put a question mark. Very small over here. I wish it was bigger. So the first thing I want to do is whenever I have parallel lines cut by a transversal, I just like to get started by highlighting my parallel lines so that I can clearly see anything that's going on here. And remember, our goal is to get closer to finding angle I, which is inside this triangle at the top. So I want to get closer and closer to being inside of this triangle. That's what's really going to help me. So I know this first. I have this 113 value, but it's really far from where I need to be in this triangle. So let's see if I see any angle relationships here that'll help me get closer to being inside of this triangle. So what I am seeing right now, because I highlighted my parallel lines and one of the transversals intersecting these parallel lines, I see that this 113-degree angle where the parallel line meets the transversal is top left. So I see that in the same position is this angle over here. So I know they're corresponding angles and they're congruent because we have parallel lines. So I'm going to just go ahead and put that in. That might be something that is helpful to us. So I know that these two angles should form a straight angle, which is 180 degrees. So I can definitely find what this angle over here should be by taking 113 and subtracting it from 180. So let me do that on my calculator, and I get 67 degrees for this angle right over here, 67. I also see a relationship of vertical angles here because remember, we also have this 80-degree angle. So we're going to want to get it closer to being in this triangle. And I see that this angle here is vertical to this angle. And we know vertical angles are always congruent, so this one is 80 degrees as well. Now we know two angles in the triangle, so we can definitely find the third one since all the angles in a triangle add to 180. We do this angle 67 plus this angle, that's 80. I got 147, and I'm just going to subtract that from 180 degrees, and I get 33 for this angle with question mark, and that's the angle that we are looking for. It does say justify each step with an angle property. So to figure out this 113-degree angle here, we used corresponding angles are congruent when lines are parallel. To find the 67-degree angle, we use the fact that angles that are supplementary form a straight angle or add to 180 degrees. You could also write down that angles that form a linear pair are supplementary or add to 180 degrees. These two angles are supplementary and right next to each other, so they definitely form a linear pair. To get this 80-degree angle over here, we use the fact that vertical angles are always congruent. And then to figure out that the final angle of this triangle was 33 degrees, we use the fact that the sum of the angles of a triangle is always 180 degrees. Let's move down and let's check out this proof, which also happens to be, I believe, the last. Oh, no, there's one more question after that. Okay. Let's take a look over here. So we have AB congruent to CD. So here's AB and here's CD. We have angle A congruent to angle D. So here's angle A and here's angle D. And our goal is to prove that BD is congruent to AC. So here's BD. I see that BD is part of this triangle BAD over here. And AC is part of this triangle ACD over here. So those are the two triangles I'm going to focus on. Whenever I'm working with overlapping triangles, a really great strategy is to draw each of the triangles separately from each other so that we can clearly see what's going on. So I'm going to draw them separately. I labeled them as they are in the diagram, and I'm just going to remark them with the given information that we already filled into the original diagram. Here we go. Okay, so remember whenever triangles are overlapping, there's usually a side that's shared between them. So I see that AD is the same in both of these triangles. So I'm just going to mark them as being the shared side. And I'm going to go ahead and get started with the givens. So my givens here are that AB is congruent to CD and that angle A is congruent to angle D. So that's given. And from our givens, we already had one of the sides that we need to prove the triangle's congruent. And we also have one of the angles. I just need the shared side by reflexive property for SAS to prove the triangle's congruent. So let me put that in. AD is congruent to AD, and that's by the reflexive property. And then we can definitely make the statement that triangle BAD is congruent to triangle CAD, and that's by SAS. And then we can definitely say that BD is congruent to AC by CBCTC. Remember, after we prove triangles congruent, the corresponding sides or angles are also automatically congruent by CBCTC. Okay, and here I have the last question. RS and TV bisect each other at point X. Prove TR is parallel to SV. So since RS and TV bisect each other, they're splitting each other into two equal parts. So RS is being split equally into two congruent parts, and TV is also being split equally into two congruent parts. I also see vertical angles here. So I know already that the two triangles are congruent by SAS. So let me get this into the proof, and then we'll talk about how we're going to prove that TR is parallel to SV. So just to not make this video go on forever, I'm just going to not write out my givens here, but you definitely should, especially on a test. Your givens are your starting points, and they are necessary. So then I'm going to put in the conclusions that we drew from the givens, so that Tx is congruent to Vx, and that Rx is congruent to Sx. And we know that because we were told that the line segments bisect each other. So we know a bisector cuts a line segment in two congruent parts. Then we mentioned the vertical angles. So I'm just going to name those. Angle TXR, 3 letters, remember, is congruent to angle SXV. And I'm going to write here vertical angles are always congruent. So remember that. And now we know that the two triangles, so let me put that in the next step. So triangle TXR is congruent to triangle SXV, and I can definitely say by SAS. Now take a look at this. What if I now say that angle T and angle V are congruent? How would you justify that? You might be thinking, well, angle T is an angle in this triangle, and angle V is an angle in this triangle, and we just proved the two triangles congruent to each other. So that makes angle T congruent to angle V by CBCTC. Remember, anytime after we show two triangles are congruent, any other angles or sides in those two triangles are also congruent to each other. That's what CBCTC means. And we're trying to prove that TR, which is right here, is parallel to SV. If I highlight them and I highlight this transversal over here that intersects those lines, I see my backwards letter Z. And we all remember what kind of angles are in the corners of the Z's. That is alternate interior angles. We learned that if we have a pair of congruent alternate interior angles, that definitely proves that lines are parallel. So I'm going to put over here, TR is parallel to SV. And my reason is going to be if alternate interior angles are congruent, then the lines are parallel. You can word that any way you want. Just make sure that you mention that the fact that we have congruent alternate interior angles here is why the lines are parallel to each other. Let me make sure there's no more questions on this review sheet before I end this video, and we are all done. Hopefully this helped.